All right, last class, we covered some of our nomenclature rules, as well as talking about different types of ions. So we've talked about ionic compounds that have a metal, which is the lower left-hand, most of the periodic table, and nonmetal, which is the upper right-hand side of the periodic table. With one notable exception being NH4+, which can be a cation, or is a cation, and we can also use that to make an ionic compound instead. I think that might show up on the homework. I don't think it shows up on an exam. So ionic compounds, metal, and a nonmetal combined. We talked about situations where we've got predictable ion charges, so thinking of our alkali metals, our alkaline earth metals, aluminum, zinc, silver. Those ones, the naming, you just say what the cation is, then you say what the anion is. Change the ending to IDE. We also had ones with transition metals that can have multiple charges, where we have to include in parentheses those Roman numerals, 1, 2, 3, 4, etc. 6 is the highest I'd expect to see. And then we talked about molecular compounds, which we're looking at here, where we use these prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And that's just the first 10. You can go up to over 100 for some of those prefixes. We're not going to do that. But there's like a lot more. So if you want to look at it, it's fun, I think. But you don't have to know it, of course. And we also changed the ending to IDE. Our third group, the last group for nomenclature that we're going to go over, is acids. Acids are a specific type of molecular compound. So what is in an acid? What kind of elements are in an acid if they're a type of molecular compound? Would we expect to see iron in an acid since it's a molecular compound? No. They're molecular compounds. They're only what kind of things? Nonmetals. So they're only going to be nonmetals, no metals. If you see a metal, it's an ionic compound. So these are molecular compounds. Acids are molecular compounds. They form ions when they dissolve in water. Our other molecular compounds that are not acids, if you dissolve them in water, if they dissolve in water, they just stay intact as whole units. They don't form ions. For acids, hydrogen is the first element in the formula. This will be true for all of the acids that you see in this class, unless I make an oopsie. Hydrogen will always be the first element. So if there's a hydrogen in front, that means in this class, it's an acid. Not all acids out like in the real world outside of this classroom have the H in front. In this class, all of the acids will have the H in front. That's your cue, your key that we're dealing with an acid. We are going to have two types of groups of acids. Our easier, arguably, binary acids. Binary acids contain hydrogen. Hydrogen will be in front. And they'll also contain a nonmetal. So from that upper right-hand side of the periodic table. Upper right area of the periodic table. We're also going to have oxyacids. The oxy part letting us know there's oxygen in there. These oxyacids are also going to have hydrogen. The hydrogen will be in front. It'll be the first thing. They'll also have a nonmetal and oxygen. The nonmetal and the oxygen together are an oxyanion. So the things that end in ate and ite that we were looking at yesterday, and they might also have per or hypo in front. So like NO3 minus is nitrate. We might see NO3 show up in an oxyacid. And we've got different naming rules for both of them. So that's why we're separating them into these two groups. So for binary acids where we just have two elements, our name takes the following form. We have a hydro prefix that we put in front. This is what is unique about binary acids. You will never see this on an oxyacid. Then we will have the base name for the anion, so kind of chopping off the back part of the name. And then we're changing the N to ic instead of ide. We've been doing ide a lot. We'll change it to ic and then add acid at the end, which is a big giveaway that we're dealing with an acid. It's in the name. So for example, HCl, HBr, these AQs just mean that they're dissolved in water. I'm explaining that in case somebody's like, why is there an AQ? I'm confused. So the HCl, we've got hydrogen, we've got chlorine. Hydrogen comes first. That lets us know that it's an acid. Right? H in front means it's an acid. It's just two things, so it's a binary. So we have the hydro prefix, the base of the chlorine, chlor, change the ending to ic acid. Same idea for HBr. We've just got two things, so we have the hydro prefix, the base for bromine, brom, change the ending to ic, acid, hydrobromic acid. Any questions or confusion so far about binary acids? All right, let's name these two binary acids. They are both binary acids because there's just two elements. We've got HF. HF has hydrogen in front. That means it's an acid. And it's just two elements. It's the hydrogen and a nonmetal, F for fluorine. Since it's binary, we have the hydro prefix, the base for fluorine, which is FLUOR, and we change the ending to ic acid. So hydrofluoric acid. Hydrofluoric acid made popular in the hit TV show Breaking Bad. Notably good at dissolving bathtubs. Questions about how we got the name for hydrofluoric acid? Anyone? All right. I want to point something out here. We are going to have a nomenclature worksheet. It's actually going to be after our first exam, which maybe I should have put it earlier, but whatever. So on that, there's a couple of words that people really love to spell incorrectly. And by love, I mean it just happens accidentally, but it's annoying to me. Fluorine, anything with fluorine in it, seems to really trip people up. Fluorine is UO, FLUORINE, right? A lot of people like to put like it's flour, like you'd use for making cakes or tortillas or whatever. Fluorine. It's not fluorine, it's fluorine. So that's one. Fe is what element? Iron. IRON. I do occasionally see people spell it how it sounds, IORN. Please don't do that. If you do them like it's not the end of the world, I'll still understand what you mean, but try to spell them correctly, please. just because it bothers me. That's all. It's just that it bothers me. So that's hydrofluoric acid. Some notes for our nomenclature worksheet and spelling in general. Now you try for H2SE. Give that one a shot. All right, H2SE. Some people get confused when we do things that have multiple hydrogens. It's still only hydrogen and one other thing, so it still qualifies as a binary acid. So H2SE, we've got our hydrogens in front. That lets us know that it's an acid. Anytime that you see an H up front, your brain, hopefully, you can train it to just scream at you, acid. And then we can get down to naming it. So we've just got two things. We've got the hydrogen, we've got the selenium. And since it's a binary acid, we have this hydro prefix. And then we do the base name, or the base of the name for selenium. So selen. Drop the ium at the end. And then our rule is that we change the ending to ic and add acid to the end. So this would be hydroselenic acid. The reason for the different number of hydrogens in front is the type of anion that the nonmetal forms, the non-hydrogen nonmetal. So fluorine, if you find it on our periodic table, it's one of our halogens. It's at the top of the halogen group. It wants to form a 1- ion because it's one space over from the noble gases. To balance out a 1- charge, you need one positive charge. Hydrogen forms a 1+ charge. So every hydrogen that we put in front counts for one positive charge. Since we have a 1 negative charge on fluorine, we only need one hydrogen in front. That's why we have HF. For H2SE, hydroselenic acid, selenium is under oxygen. It would form a 2- charge because it's two spots over from our noble gases. So this would be Se2-. To balance out a 2- charge, you need a total of a 2+ charge. Each hydrogen is one positive charge, so we need two of them. So to get things all balanced out, we need two H+ to balance out the Se2-. So it's sort of like putting together an ionic compound, but because it's only nonmetals, it's a molecular compound. It's just that acids also dissociate when they go into water or dissolve into other things. So that's the reason that we've got two hydrogens there instead of just one. So that's binary acids. Our oxyacids are a little bit more involved. So our oxyacids contain oxyanions, things that end in -ate and -ite, if we're looking at the names, or things that have a nonmetal and then some oxygens right next to each other. And we've got a whole table of them on the top of your green sheet. So a bunch of all the 8 forms are up there. That's the ATE endings. So for example, HNO3 contains the nitrate ion. Nitrate has a 1- charge, so we have one hydrogen in front. So again, we're balancing these charges based on the charge on the anion. Maybe if I circle that, it's a little better. Right, one negative charge. H2SO3 and H2SO4 both have either the sulfite or the sulfate ions, oxyanions. Those have 2- charges. And so we have two hydrogens in front. It's just to balance out our charges so that we've got a neutral molecule. For example, phosphate, PO4 3-, it's got a 3- charge, and so we need 3 H+ to balance that charge out. We've got two different rules for our oxyacids. if we have an ATE ending, that ATE ending turns into IC. So like nitrate. If that's in an oxy acid, would be nitric, and then add acid. Our other rule is that things with the ITE ending change into an OUS ending. So nitrite, another oxyanion, would change to nitrous acid. So 8 turns into ic, ite turns into us. That's our rule. Notice that there's no mention of per or hypo. We don't remove or change per or hypo if we have those. So an example, perchlorate, which is ClO4 minus. If we make an acid out of that, this will be perchlor, change the ending to ic, and add acid. So perchloric acid. We could also have hypochlorite, which would turn into hypochlorous acid. And it's not one of our examples, I was just making sure. So hypochlorite, which is often an ingredient of bleach. ClO minus, if we turn that into an acid, that would be hypochlorous acid. That ITE turns into OUS, just like the ATE turns into IC. So really, the tricky part, I think, for oxyacids is figuring out, especially if you're given a formula, like HNO3, figuring out what does the NO3 get called? What's the name for it? And then remembering either of our two rules. 8 turns into ic, or ite turns into us. So let's work through these. HNO3, we see that it's not just two things. We've got oxygen in there. So we would go to our green sheet, or go to a table, or we'd have it memorized and look up NO3. So go find NO3 on your green sheet. Or we would find something that looks like NO3, so NO and then some number of oxygens. What do you find on your green sheet? NO what? How many oxygens? NO3. And what is that called? It's called nitrate. So the NO3 here is nitrate. I also overlooked, it's got the H in front, so it's an acid. So it's an acid, and it's made with nitrate. Nitrate's in it. What's our rule for things that end in 8? How do we change them? 8 turns into what? Yeah, 8 turns into ic. So niter, ic, and add acid to the end. For H2SO3, we can identify that it's an acid because of the hydrogen in front. And then we need to find on our green sheet something that looks like SO and then some number. SO, some number of oxygens. What do we find that looks like that? SO what? SO what? SO4. We find SO4. So we've got SO4, and that's the 8 ending. We're only given the 8 endings. We have SO3. So how do we need to change our name to accommodate the change in oxygens? If the SO4 2- is sulfate, what is the SO3 2-? Not putting it into the acid yet. If SO4 2- is sulfate, we remove 1 oxygen, what does it become? SO3, what do we call it? Still sulfite. So it's sulfite that we have, SO3, and we change the ending when we make it an acid. And this is a little bit of a weird one. So instead of just changing to sulfous acid, it's, for some reason, sulfurous acid. So I'll put that UR part in blue. Sulfurous acid. If you write sulfous acid, probably most chemists will understand what you mean. Probably. Questions about naming either of these oxyacids? All right, to show you possibly why we've got the hydro prefix on our binary acids, let's look at an acid that's interesting. Sorry, my brain was just making some connections. Let's look at if we had H3N. What kind of acid is that? Is it a binary acid or an oxyacid? Do we have oxygens? No oxygens. Do we have just 2 elements? We do have just 2 elements. So it's a binary acid. Our rule for binary acids, right, we put this hydro at the front. And then we have the base for nitrogen, NITR. And we would change the ending to ic acid. If we didn't have that hydro at the front, then our HNO3 would be nitric acid, and our H3N would also be nitric acid. So that's probably part of why we have that hydro prefix that we need to include for our binary acids. Otherwise, you'd get the 2 confused. In chemistry, all of our names should specify exactly 1 compound. There shouldn't be any ambiguity like, oh, it could be this or it could be this other thing. We always want it to point only to 1 specific thing. We don't want any ambiguity about what we're talking about with these naming conventions. All right, some oxyacids to try. We've got HNO2, we've got HClO4. I'll give you 4 minutes or so. That was about 3 minutes. So let's get to naming. HNO2 is an oxyacid. We know that it's an acid first and foremost because there's hydrogen in front. Hydrogen in front means that it's an acid, and we've got an oxyanion, NO2. So we'd have to find on our green sheet or have memorized something that looks like NO2, which would be NO3- on our green sheet. This is nitrate. The way that we've changed from our ATE ending to this NO2 is we've dropped 1 oxygen. We have NO2-, and so that means that we have nitrite. And our rule when we turn it into an acid is that this becomes us, O-U-S. So the ite turns into O-U-S, and we add acid at the end. So this is nitrous acid. For HClO4, we know that it's an acid because it's got hydrogen in front, and it's got an oxy anion, ClO4, on it as well. So we would go find something that's got chlorine as an oxy anion, and that would be ClO3 minus. ClO3 minus would be our chlorate. And rather than taking an oxygen off, we've added an oxygen. So we've got ClO4 minus. And when we add one to our ate form, we have to add the prefix per. Per, like in hyper. So this is perchlorate. Perchlorate, and we can turn that into the acid form. The per stays on there. Doesn't change. We've got the chlor part, and we change the ate ending to ic and add acid at the end. So this is perchloric acid. Questions about naming either of those? All right, all of our naming conventions for the class show up on this table. It's not my favorite version of the table. I had a different version of the table, but it's from a different book that you have to pay money to use. So we don't have that one anymore. But the basic idea is we've got 3 different categories. We've got ionic, molecular, and acid. Those are our 3 big types of chemicals that we will be naming in this class, or that we'll be expected to know how to name in the class. We can tell that something is ionic because it's got a metal in it. It also has nonmetal in it, but the big key for ionic compounds is that we've got a metal in it. We also have our molecular compounds. Here it says covalent compounds. Our molecular compounds are nonmetals only. So there's no metal. And those are differentiated from our acids because our acids have H in front of the formula. Within our ionic compounds, we name our cations first. We've got 2 types of cations. Cations with only one ion, so they only form one possible charge. It's just the name of the thing. So like magnesium, aluminum, rubidium. Nothing special, nothing fancy about it. And then we change the ending to "ide" for the second thing. So we change the nonmetal to end with "ide." And that's true for both types of cation options. For cations, positively charged ions with more than one, we'll say 2+ to save room. Like iron, if there's an iron 2+ in there, iron, and then we have to use parentheses, put the Roman numerals with the charge in it, and we still change the ending of the nonmetal to the IDE. If it's got a polyatomic ion, so like if it's Fe2+, FeNO3, 2, we don't change the ending of our oxyanions or our polyatomic ions. So this would be iron 2 nitrate. That "ide" ending lets us know that we've just got that nonmetal by itself. An example what that would look like, Fe3N2 would be iron 2 nitride. The IDE ending because it's just one nonmetal. All right, let's try to not get caught up in the weeds as much on the molecular compounds. Molecular compounds, we've got nonmetals only, and these use prefixes. Our one little caveat is that we exclude mono for first element. So whatever comes first, we don't include the mono part for that. Otherwise, it's the mono, di, tri, tetra, hexa, penta, all that sort of good stuff. And then we just talked about our acids. We've got oxyanions. We've got just one nonmetal for our binary. If it's binary, it's got the hydro prefix. If it's from an oxyanion, our rule is ate turns into ic. Ite turns into us. So we got a lot of stuff going on, but there's some key identifiers that hopefully I've pointed out enough times. Hopefully you've written them down. There's some key identifiers that set all of these groups apart. When you're really good at it, once you've got a lot of practice, I don't expect you to get to that point in this class. Once you've got a lot of practice, you can just kind of look at the formula and you've got the name immediately. I usually try to say the name and also just the formula, read the formula out because it helps us get a little bit of practice. All right, and then the last slide for this chapter. Some more stuff for you to try. This is combining all of our naming conventions. So all of our nomenclature all in one spot so that you don't know automatically what kind of thing we have. So go ahead and give these a shot. I'll give us 10 minutes to do this and then we'll launch into our break after that. So if you finish early, you can have a longer break and we'll go over it at the end and then wrap up. So we've got 5 chemicals here, and we need to name them. The first part of naming a thing is figuring out what kind of chemical it is. So that's where we want to start. We want to categorize it. I'm thinking of this sort of a flow chart, right? We want to work our brains step by step through each of these parts. So first we want to figure out what kind of chemical it is. Then we want to think about, do we have multiple types of chemicals within that? Or do we just jump to the name? So for the first one, for A, we have PCl3. What kind of elements do we have in PCl3? Or what kind of compound is it? Phosphorus is one of them. What kind of chemical is phosphorus? Is it a metal or a nonmetal? It's a nonmetal. Our metals, if we have one up first, nonmetal. So this is nonmetals only. And that means it's either an acid or a molecular compound. For it to be an acid, we would have to have H in front. We don't have H. So that means that it's a molecular compound. So it's a molecular compound. And our special part about molecular compounds is prefixes. So this is a molecular compound. We need to add prefixes based on the number of each thing that we have. For our first element, the phosphorus, we have one of them. And our rule is that if it's the first one, we omit the mono. So this is just phosphorus. look at our other thing, we've got chlorine, and we have 3 of them. Our prefix for 3 is tri, T-R-I, and then we put the base name, chlor, and change the ending to IDE. So this is phosphorus trichloride. For our second one, HClO, we have hydrogen in front. Hydrogen in front is our giveaway that it's an acid. We've got 2 possible types of acids. We've got binary acids, just 2 things. We have more than 2 things, so that must mean that we've got an oxyacid. Oxyacids have an oxygen in them and some other nonmetals. So we've got this ClO, that thing lumped together, ClO. We would go to our green sheet, find something that looks like ClO. What do we find that looks like ClO on our green sheet? ClO something. Chlorate, ClO3 minus is chlorate. We need to go through step by step. How are we changing this name to get to just ClO? Because we've got 3 oxygens, we need to lose 2 oxygens. If we lose 1 oxygen, what happens to the name chlorate? What does it become instead? Chlorite. And if we want to take another one off, we can't do chloridite. We have to do something else. We have to add a prefix. So ClO minus would be what? Hypochlorite. So hypochlorite is the one that we've got here. ClO. So we take our hypochlorite and we change the ending. The ITE turns into OUS. So hypochlorous, and we add acid at the end. Hypochlorous acid. Then we've got, for C, CaOH2. What kind of compound is CaOH2? Is it ionic, is it molecular, or is it an acid? Do we have H in front? No, no H in front, so it's not an acid. So it's either ionic or molecular. If it's ionic, it has a metal. If it's molecular, it doesn't have a metal. So looking at Ca, is Ca a metal or a nonmetal? Ca is one of our metals. Ca is an alkaline earth metal. So that's a metal. That means that this is ionic. So we've got an ionic compound. We've got 2 possible options for naming with ionic compounds based on our metal. We've got metals that form only 1 charge, metals that form more than 1 charge. Which group does calcium fall into? Does it form 1 type of ion or multiple types of ions? Does it have the same charge every time, or can it have different charges? How about this? What's the charge on calcium? If calcium's an ion, what charge does it have? 2 plus. Is it ever going to be anything other than 2 plus? It's not. We know that it's 2 plus because it's one of our main group elements, right? It's over here. It's in our alkaline earth metals. It's not in our transition metals. So it's one of our main group elements. It's always going to be calcium 2 plus. Just the fact that you can name like, oh, it's 2 plus, that means that it's always the same thing. So calcium only forms calcium 2 plus, so we don't have to specify the charge, just calcium. And then we've got OH. What is OH? It's a polyatomic ion. It's hydroxide, calcium hydroxide. For D, we've got what kind of compound? Do we have an H in front? No H in front, it's not an acid. So we've either got an ionic compound or a molecular compound. What kind of element is nickel, Ni? Is it a metal or a nonmetal? It's a metal. So nickel is a metal. This means we've got an ionic compound. What's the charge on nickel? If we just have nickel by itself and it's an ion, what's the charge on the nickel? Do we know? We don't know. Nickel is one of our transition metal elements. You can find it in group 10, Ni. We don't know what the charge on the nickel is, just based on where it is on the periodic table. So we have to figure it out, which means we get to do a little bit of algebra. So looking at our anion, our PO4, PO4 is what? Phosphate, which is an oxyanion. What charge does phosphate have? PO4 what? It's on the green sheet. 3 negative, 3 minus. So PO4 3 minus, and we've got 2 of them, right? So we've got a total of 6 negative, 6 minus from phosphates. Our ionic compound, the whole formulae, has to have a neutral charge. So the phosphate charge, the 6 minus, has to be balanced out by the nickel's charge. So total is 6 minus. We need to balance that out. That means that we have a total of 6 plus from 3 nickels. So if we've got 3 nickels, they each have the same charge, and it adds up, multiplies out to a 6 plus. What's the charge on each nickel? We've got 6 plus charge. We've got 3 of them. 6 divided by 3. Each nickel must be a 2 plus charge. And that's the piece that we were missing to be able to name this, since it can form multiple charges. So nickel, specify the charge in parentheses of 2, and then the name of our oxyanion, phosphate. And then lastest but not leastest, we've got HF. What kind of thing is HF? Kind of compound? Binary. Binary what? Binary acid. It's got H in front, so it's an acid. It's just 2 things. So it's binary. What's special about binary acids? What do binary acids have that all of our other names don't have? Hydro. So they start with hydro, and then we have the base name for the thing that's not hydrogen, which is fluorine. Hydrofluor, not hydroflower, and change the ending to ic and add acid. Questions about any of these namings? Then we will stop there for chapter 3.